Welcome back. Here is an example to test mu when sigma is unknown. The drug 6-MP is used to treat leukemia. The following data represent the remission times in weeks for a random sample of 21 patients. So 21, sample size is 21. Okay, so there are these 21 patients and their remission times in weeks. The sample mean is 17.1. How do you find sample mean? You add all the numbers, divide by the total number. In our case, 21. And sample standard deviation is 10. Let x be a random variable representing the remission time in weeks for all patients using 6-MP. Assume the distribution is mound-shaped and symmetric. You see, because we assume this, our sample size of 21 is okay. If we didn't have this assumption or that x is normal, such assumptions didn't have, then sample size has to be minimum of 30 for us to proceed. A previously used drug treatment had a mean remission of mu 12.5 weeks. So that is your null hypothesis already. Do the data indicate that the mean remission time using the drug 6-MP is different, that is either way, from 12.5 weeks? Use alpha, that is level of significance, to be 0.01. Okay, so this is going to be two-tailed. Step 1, establish the null and alternate hypothesis. That's your null hypothesis. H0 mu equals 12.5 and H1 is mu not equals 12.5. So you're looking at time, mean remission time that is different from that provided, right? So mu not equal to 12.5. B part, check the requirements. What distribution do we use for the sample statistic? T. Compute the sample test statistic from the sample data. The X distribution is assumed to be mound-shaped and symmetric. We don't know sigma, so we use student's T distribution. Degrees of freedom 20. How is this 20? Sample size minus 1. 21 minus 1. Okay. Now X bar is 17.1. The standard deviation is 10 approximately. Mu is 12.5 and N is 21. Using all that, you get T X bar minus mu all over sigma over square root N. So T comes to about 2.108. Now, 2.108 and negative 2.108. So you need the p-value. Find the p-value or the interval containing the p-value. Now, use table to find an interval containing the p-value. You need 2.108. Okay, you are going to look for the split one. So, let's see. This is a two-tailed test. We use entries from the row headed by two-tail area. So, you have in your table, let's look at our table. On the top, you have one tail and you have two tail. You are looking at two tail. All right. You are looking at two tail. Degrees of freedom is 20. And my p-value, so, and sample statistic is 2.108. Now, 2.108 falls between 2.086 and 2.528. It falls between these two. All right. So the p-value for the sample T falls between corresponding two tail areas. 0.050 and 0.020. So you're looking at 20, you see, and T 2.108. T 2.108. So I'm on 20, 2.108. There you go. So there. All right. So two-tailed gets me 0.050 and 0.020. These are the two options I get. Okay. So my p-value is between these two. Okay. What next? Conclude the test. My p-value is between these two values. The following diagram shows the interval that contains the p-value corresponding to the test statistic. Note that there is just one p-value corresponding to the test statistic. Table 4 of the appendix does not give that specific value, but it gives you a range. All right. Alpha is kind of on the left. As the diagram shows, the entire range is greater than alpha. This means my p-value, which will live between these two numbers, is greater than alpha. Whenever our p-value is greater than alpha, we cannot reject H0. Okay. Using the raw data, computer software gives p-value to be approximately 0.048. This value is in the interval we estimated. It is larger than the alpha value, so we do not reject H0. What is our interpretation? Our interpretation is that at the 1% level of significance, the evidence is not sufficient to reject H0. Based on the sample data, we cannot say that the drug 6-MP provides a different average remission time than the previous drug. Okay. Part 3. Testing mu using critical regions, that is called the traditional method. The most popular method of statistical testing is the p-value method. For that reason, the p-value method is emphasized in our book. Another method of testing is called the critical region method or the traditional method. For a fixed preset value of the level of significance alpha, both methods are logically equivalent. Because of this, we treat the traditional method as an optional topic and consider only the case of testing mu when sigma is unknown. All right. Consider the null hypothesis H0 mu equals k. We use information from a random sample together with the sampling distribution for x bar, level of significance alpha, to determine whether or not we should reject the null hypothesis. The essential question is, how much can x bar vary from mu equals k before we suspect that H0, null hypothesis mu equals k, is false and rejected? The answer to the question regarding the relative sizes of x bar and mu, as stated in the null hypothesis, depends on the sampling distribution of x bar, the alternate hypothesis H1, and the level of significance alpha. If the sample test statistic x bar is sufficiently different from the claim about mu made in the null hypothesis, we reject the null hypothesis. The values of x bar for which we reject H0 are called the critical region x bar of the distribution. All right. Let's figure out what that means, right? Depending on the alternate hypothesis, the critical region is located on the left or on the right or on both sides. So, left-tailed area is here right-tailed area is here, two-tailed area is here. So notice area is alpha over 2 here, alpha over 2 here, and then total area is alpha. Okay. So notice I'm looking for area alpha overall. Okay. Notice that the total area in the critical region is preset to be the level of significance alpha. This is not the p-value discussed earlier. In fact, you cannot set the p-value in advance because it is determined from a random sample. We know that the level of significance alpha should, in theory, be a fixed preset number assigned before drawing any samples. So, we are using alpha because we haven't even drawn any samples. Okay. So critical region, the most commonly used levels of significance are alpha 0.05, alpha 0.01. Critical regions of a standard normal distribution are shown. Okay, so this is for 0.05, that is your value, critical value. Alpha 0.01, that is your critical value. Now these are left tail distributions, right? And here are right-tailed distributions. And here is two-tailed distributions. Okay, alpha 0.05 are these ones, alpha 0.01 are these ones. Okay, for easy reference, they are also included in table 3 appendix. So let's look at our table. Here, levels of significance, alpha 0.05, alpha 0.01. Left-tailed, right-tailed, two-tailed. Okay. Now, the procedure for hypothesis testing using critical regions follows the same first two steps as the procedure using p-values. However, instead of finding a p-value for the sample test statistic, we check if the sample test statistic falls in the critical region. If it does, we reject H0, otherwise we do not. So we are looking for sample test statistic, whether it falls in your critical region. So what is the approach? First, when sigma is known, you first set your significance level alpha. Alpha is typically 0.05 or 0.01. Use your X bar from the sample test, mu from the null hypothesis, sample size n, use the known sigma and find sample test statistic Z. X bar minus mu all over sigma over square root n. And then show the critical region or values on a graph of the sampling distribution. Okay. The level of significance alpha and the alternate hypothesis determine the locations of critical regions. Conclude. If the statistic is in the critical region, reject H0. If the statistic is not in the critical region, do not reject H0. Interpret. Okay. This will be better understood with an example. Okay. We'll come to the example in our next video.